Every single day, we tap, swipe, and scroll, our fingers flattening against sleek, glowing screens thousands of times. But chemically speaking, the standard glass sitting on top of your device is completely inert. It's a flawless insulator that blocks electricity and possesses zero capacity to sense biological contact. This creates a puzzle. How does a cold, inanimate sheet of minerals recognize exactly where your thumb lands in a fraction of a second? The glass acts as a protective window into a microscopic, high-speed translation engine hidden just beneath the surface. If we zoom in and descend beneath that protective layer of Gorilla Glass, we enter a microscopic void. Here, we find a transparent sheet of conductive material, usually a compound called indium tin oxide, etched into a highly precise horizontal and vertical grid. A controller chip located deep inside the phone continuously pumps a tiny, uniform electrical charge through every single intersection of these microscopic wires. The screen broadcasts an invisible energy field across this grid, waiting for an outside object to steal its power. Because humans are mostly water and dissolved minerals, our bodies act as natural electrical conductors. The exact millisecond your skin makes contact, your finger draws a tiny fraction of that electrostatic charge away from the grid, hoarding it at the physical point of contact. Sensors lining the corners of the screen detect this precise drop in voltage, routing the data through metallic pathways to calculate the exact X and Y coordinates of the disruption. While early touchscreens could only track a single point of contact, modern devices utilize a system called mutual capacitance. By calculating the electrical drop at individual intersections rather than across entire rows, the device can track multiple simultaneous inputs independently, enabling complex gestures like pinching to zoom. In this system, your phone maps the microscopic void of electricity your body creates, rather than the physical pressure of your finger. This reliance on electrical transfer causes capacitive screens to fail when a non-conductive barrier, like a winter glove, is introduced. Standard fabric acts as an insulator, preventing your body's natural conductivity from ever disrupting the device's electrostatic field. ATMs and industrial machines solve this by abandoning electricity in favor of mechanical force, utilizing a technology called a resistive touchscreen. These screens use a flexible top layer suspended over a rigid bottom layer, kept apart by a grid of tiny insulating spacer dots. Physical pressure forces these two conductive layers to touch, completing a circuit that identifies the exact coordinates of the collision. Capacitive technology relies on electrical synergy with the user, while resistive technology functions through blunt physical contact. Other invisible sensor networks exist outside these two standards. Infrared displays, for example, map your input by breaking a microscopic web of intersecting light beams. Surface acoustic wave technology tracks the disruption of ultrasonic ripples traveling across the surface of the glass. These robust alternatives are deployed in high-impact industrial environments where delicate capacitive glass would be too fragile to survive. Whether utilizing electrostatic fields, physical pressure, or ultrasonic waves, every touchscreen serves one vital function: translating the analog movements of humanity into the binary code required by machines.